point 3. Right, and so let me write down, remind you once again about the final statement about homogeneous spaces. So G was a connected algebraic group. Then what did we want to say? That if you have a homogeneous space for G, then homogeneous G space, then X is irreducible and moreover smooth. So the proof of this is it's irreducible because it's a homogeneous space for G. So if I take an orbit map of any point in X, it's going to be 1 to X, and G is connected, therefore irreducible, therefore X is the continuous image of an irreducible space, therefore irreducible. And why is it smooth? Well, X being homogeneous every point looks like every other point, and we know from something that we will prove today that if you have a then that has a smooth point. There is always a smooth point. In fact, that is enough to prove for affine varieties, because every variety for us is a union of affine varieties. Therefore, if a point is smooth, so if you have a variety, it is covered by, it has open sets which are isomorphic to affine varieties. So if I take an open set and that is an affine variety, and if I show that every affine variety has a non-trivial simple point, that will show that every variety has a simple point. So secondly, that if X to Y is a map of homogeneous spaces, G is a G map of homogeneous spaces, homogeneous G spaces, then as pointed out last time, as Shantha observed, this is always going to be onto. Therefore, you can talk about, so therefore it's in particular it's a dominant map. Therefore, the field Ky embeds into the field Kx, right? And so we can talk about separability. So then X to Y is separable. If and only if d phi x is surjective for some x, and that's if and only if d phi x is surjective for all x and x. Okay, and then once again that will follow just from we'll prove today what we will show is that, so this is separable if and only if there exists a simple point x with whose image is simple in y, is a simple point of y, such that the homomorphism is surjective. So given that, since every point of x and every point of y is simple, if this is true for some point x, you're done. That will show that this is separable. Okay. Moreover, we will also show that if x to y is separable, then the points x, the points x in x, such that the tangent space map is surjective, and let's see, do I want to say and such that phi of x is simple and the tangent map space is surjective. So all three conditions: x is simple, its image point is simple, and the tangent space map is surjective. That's an open set, non-empty open set of x, and therefore we'll always assume irreducible. Therefore, in particular, it's a dense open set as well. Okay. So if this is separable, then surely there is a map, there is a point where this is surjective. In fact, it's a dense thing, but every point looks like every other point. Therefore, this is in fact this is true. And finally, if G to G prime is a surjective homomorphism of algebraic groups, so call this again phi, then phi is separable if and only if d phi e is surjective. That is a special case of this, where you think of G prime. G is of course a homogeneous space for itself by left multiplication if you wish. G prime, this is a surjective map, so you can think of G prime also becomes a homogeneous space for G, and so therefore you can apply this and you have at the identity. Okay, so we are reduced to showing the following. So let me write out this lemma. So the notation is, so X is an irreducible affine variety, and then I have this is the ring of functions. A is my M cross N matrix with entries in Kx. So this is a free module of rank M, this is a free module of rank N, and by an appropriate convention, thinking of these as row matrices, row vectors, elements here as row vectors with entries in Kx, I can denote this map by an M cross N matrix. Okay, and then I denote, so he denotes by M of A. This is so this is the co-kernel of this map A. So we will abuse notation and think of A as a map, A of A as a matrix, and we will also use similar notation for other derived objects. Okay, with this notation. Okay, now also let R be, so I can let R be the rank of A over I put K round bracket X. Okay, so think of, so that's a field. So I can think of A as a matrix with entries in a field, and then the notion of rank makes eminent sense. It is the column, is the dimension of the column space, or the dimension of which is equal to the dimension of the row space, or which is also equal to the maximal dimension of a R is the maximal dimension of a square matrix, square submatrix of A with non-zero determinant. Okay. Then, okay, now to the lemma. This is the notation. Okay. The thing is, so dimension is n minus r. So what is this? This of course means co-kernel of this matrix over Kx. Okay. Now that's a easy fact, right? This has dimension n. This has rank r, which means the image is a subvector space of rank r. Therefore, the co-kernel is just a quotient of that. N is n minus r, right? So this is just from linear algebra. Okay. 2, the set of x in X such that dim K Mx Max is equal to n minus r is open and non-empty. Now here the notation means when I pass to the, so what does this notation mean? This means I can go modulo the maximal ideal at the point x, and I will be getting into, so I look at, so you read this matrix modulo the maximal ideal at x. So I can, by doing that, I can think of it, it becomes a matrix over K. And then I have a field, and then I can take the rank of that. The claim is that right, so okay, so once again that the dimension of this co-kernel, where once again over a field, is n minus the rank of this matrix A
I can looked at as a matrix here, correct? That's obvious. That's because again we are over a field, and this will have vector space dimension n when I go there, and whatever the rank of this is, I'll have n minus the rank of that, right? Okay. Now, obviously, it cannot be. The claim is it cannot be any more than this, right? Such a rank cannot be any more than this. That's clear, because if something is non-zero in a quotient thing, then it is non-zero. See, the map from A to, so what are we saying here? R is the maximal size of a matrix, square submatrix, maximal size of a square submatrix of A with non-zero determinant in Kx. But instead of saying non-zero determinant in Kx, I might as well say non-zero determinant in Kx, because the map from Kx to its ring of quotient field is injective. So if it is non-zero here, it's going to be non-zero there. Therefore, I might as well say it's non-zero here, right? So what it means in particular is, if I take anything bigger, then it's anything bigger meaning any submatrix of size r plus 1 or larger, square submatrix of size r plus 1 or larger, its determinant is going to be 0 even in Kx. Therefore, surely it's going to be 0 anywhere, in particular in this, right? So this dimension is maximum value is this, okay? So what we are saying is it is actually equal to its maximum possible value on an open set. In other words, good things happen, bad things are limited to a closed subset. This is the point. Okay, so that's what we are saying. Let's see how to do this. So what's the proof of this? Maybe we saw it last time also. So okay, suppose X has this property. What does that mean? That means one of the R by R submatrices has non-zero when I pass to, it's non-zero here, moreover it's non-zero here as well, okay? Now, all I can do, I could just take that take that f, call that f. So let f be, so the proof is let f be the determinant of an R by R submatrix of A such that f of x is non-zero, right? Such an f exists because we have this, right? And now I can just do now on df. By that we mean the open set where f does not vanish, any point there will have this property. Okay, for now on df we have, or now, or for y in df, dimension over k of m a y is equal to n minus r. Right, it is less than or equal to n minus r in any case. Did I say that correctly? No, bigger. Oh, the rank can fall. Sorry. which way does it go? So R could becomes, the rank could becomes, n is n minus the rank could be, it's bigger than or equal to this in any case, it's bigger than or equal to this in any case, and it is less than or equal to, because f y is non-zero. So the rank will hit R on. Okay, so that proves number 2, because that df is an open set containing x on which this property holds. So we have proved that if x belongs to that set, then there is an open set around x belonging to that subset. So it's open and non. And oh, why is it non-empty? Well, okay, non-empty because one of those f's is, okay. So the fact that there is one of the f's which is maybe I will not write it down, but I will just say one of the f's is non-zero, and on that f, for example, take df, that will be true. So maybe I should just say this is okay, such that f is non-zero. Well, okay, maybe I should, just thinking of how to write it efficiently, maybe the first, to say it's non-empty, just choose an f without reference to any little x such that it's non-zero, and on df it's okay. So let's do, is that all right? Pardon me?
At the end we use natural substrate to show it. So we need algebraically closed. We are using that if the determinant is, if that as a function, if that element is.
Where are we using Nullstellensatz? Of course, I mean, we are using it in the sense that this is k. No, but let's see.
So f is the determinant of some R by R matrix.
Yes.
And this as an element of kx is non-zero. Now we want to say that there's some point at which it is non-zero. That means zero set of.
Okay, you are right. Of course, there many need not be. Yes, yes, of course. I mean, x need not have a point at all. I mean, to take an extreme case, yes, absolutely. I mean, we are not even sure that otherwise that x itself need not have any point, right? X could be meaning if I take a field, it could be that x has no points on that field. For example, x square plus y square plus 1 equal to 0. If I take that variety, it won't have any real points. So indeed, so yes, in that sense we are using, that's implicit, yes. Okay, so finally, if x is in X and dimension of k, m a x is equal to n minus r. So if it belongs to this open set, then there is f in kx with fx non-zero such that when I look at this localized at f, this is a free kxf module of rank n minus r. Okay, if you, okay, just so that so let me ask you a question here. So suppose I take an x in which this one does not hit n minus r but is larger. Right? Suppose the dimension is n minus r plus 1, say. Okay, r refers to the rank of this. R is fixed, n is fixed. Right? N is the number of columns of this matrix. R is the rank. These are fixed. But suppose I take a point x such that it is n minus r plus 1 or something larger, say n minus r plus 1. Then could you say this, where of course I have to make this n minus r plus 1. I mean, I am asking that question just so that you don't think there is something to be done here. I mean, it might what I'm saying is the point here is this is true only for x belonging to this open set. Okay, so if I take some other x not belonging to this open set where this is larger, then you will not be able to find that f. Okay, so what is the proof of this? Well, I mean, so proof, choose f to be the determinant of an R by R submatrix of A such that f of x is non-zero. That you can do by this, right? This means that one of the R by R minors is non-zero. So I choose that. Now, by imagine, just for simplicity, imagine that to be the top R by R matrix, north west corner, and then you can do row and column operations and clear, so say this is our R by R matrix, and you can, as we observed last time, you can make this to be 1 by doing row and column operations, and I can make this 0, make this 0, right? And the point is this has to become 0 because it can't have bigger rank. Okay, so this is 0 because that's the crucial point, right? And therefore, now what does we are done, all this, where are we doing this? All this is, we are doing it in KXF. Right, because why am I able to do it in KXF? As long as the determinant is an unit in some ring, I'll be able to do it, right? Because I invert this, I'll be able to find the inverse of this matrix, and therefore I can do appropriately make this 1 1 1. Once I make this 1 1 1, I can kill off all the columns and kill off all the rows, and this is forced to be 0. So this happens over kxf. Now, by doing row and column operations, I am not changing the module, right? I am not changing m of a, right? But what is m of a? It is this n modulo the module generated by the first few free generators, right? The images of, so it is precisely, if E1, E2, if in the basis in which my matrix looks like that, I can say, okay, in the basis, in a basis in which the matrix of A over kxf looks like this. It has this form. What do we know? The M A F is isomorphic to kx E r plus 1 I should put a kxf. Right, so that it's, therefore that's a free module. Yeah, so maybe you should try an example where, I mean, it's rather trivial once you see it, but it's important. I want to emphasize the point of this is that it's important that this be 0. That's a crucial point, right? And so what is being used here is that this is R, right? It is not that okay, so right, so we have fully proved this lemma, and now I'm going to write down 4.3.3, which is what we want to prove. So x is irreducible. Let E be equal to dimension of x. Looks like a strange choice of letter, but anyway, he's using that. If x is a simple point of x, there exists an affine neighborhood u of x such that is a free Ku module with a basis dg1 dge for suitable gi in Ku. Okay, let us okay, so we will need a slightly, so looking at this, maybe maybe last time also we did this. Okay, let me write this, and we will probably need some slightly stronger version of this to say this. So I will not erase this, but keep this and make a slightly stronger statement that we will need, which is necessary for this. To the simple points of X form a non-empty open subset of X. Three, for every x in X, dimension of Txx is bigger than or equal to E. It is at least the dimension of the variety. I am assuming X is irreducible. For simple points, of course, our definition is that when it's equal, you call it a simple point. So for most points, that is on a non-empty open set, equality holds. Okay, let's prove this. So may assume X is affine. Right, that part is goes as follows. If I prove all the statements for affine, then it will follow for any variety. Why? Okay, let's look at it one by one. If F is a simple point of X, there exists an affine neighborhood U of X such that something happens. Now, if I prove it for an affine variety, so given my, so let's see one. I look at the hypothesis X belongs to X, right? Now, since X is a variety, I can find open subset of X. Y is an affine variety such that X belongs to that. Okay, and since this is open in here, this is that's irreducible, so this is also irreducible. Okay, and there exists, now apply this, there exists an affine neighborhood of this where this holds. So there is a U open in here, but then that is going to be open in X because it's open in open and it's affine. So this will be true. Dimension of Y will equal dimension of X because it's an open variety. Open. It's open in that. Yes. Yes. So E will continue to be the dimension of. Okay. So let's look at second. The simple points of X form a non-empty open subset of X. Now, the simple so you why so to prove the second part for any variety, assuming it for affine varieties, is so write X as a union of Y's, where Y's are affine, right? Now, the simple points, now if I look at the X, let's say simple points, let me call it S, is union of Ys. Do you agree with that? Well, let's see. A point of, if it belongs to one Y and it's, so the simplicity does not matter which open set you look at. So in other words, Tx, T of X of X is the same as T of X of Y if X belongs to an open set Y of X.
How is TX defined for
Tx was mx, well, it was dimension of, okay, so you could take, one of the things was that does not change, that Ox is local around X, right? It does not change. Okay, let's see. Or if you want to think slightly differently, see, what was it? It was dir k, kx, k, right? That was this is Txx for us. Now, if a point belongs to, so this was when I'm thinking of affine, right? Okay. Now, suppose a point belongs to y1, which is affine, a point belongs to y2, that is affine, then I can find something which is affine and contained in both y1 and y2. Okay, of the form d of f. So it's d of f in y1, d of f in y2, and it's contained there. And therefore, and observe that if I localize this at any point where x is non-zero, this will not change, because see what what are derivations going to be? It will have to follow. Once I know where elements of kx will go, elements of kxf are determined by the quotient rule. Okay, so they are uniquely extendable also. So by that lemma, you can easily see that derivations, there is a one-to-one correspondence between derivations of this and derivations when I put an f here, provided fx is non-zero. Right. So using that also, you can see it does not matter which I can, of course, intuitively, once it's a tangent space, we know that it should matter only locally, but of course that is not a, you have to make sure that your definition matches with the intuition. I cannot say, look, here is the definition and it's supposed to be the tangent space, therefore it should be all right. So your question is valid, but okay, but for the moment, granting that, I can write this. It does not matter which y it belongs to, and here it is non-empty open, right? So therefore, it is non-empty open here, okay, because these are open in y, okay. Right, and that will also follow, because I can go to a y and there the E will not change, and if I put Tx of y is bigger than or equal to E, Tx of y is the same as Tx of x, that's bigger than or equal to E. Okay, so we've done this. Okay, now so I write Kx is equal to Tm you should choose the G, but anyway, so this is what he writes, M. So you're thinking of x maybe as embedded in am, with the ideal of x being generated by f1 through fn. Okay. Then what do we know? What we know, we want to apply this, right? So what we know is that I want to write m of this is this m, this A, where let's see, so okay, I'm going to erase this. So this is definition, and this one, this A is given by del F1 by del X1 or del T1 del F I hope that's correct. Let me see, just check if this is matches the, oh, this is F1. Oh, okay, let's see if that matches what we have. I'm not, oh, he seems like he screwed it up, right? He says M cross N matrix di dj fit. So the ijth entry is so what are the, so what do I know? I know that it is this No. He got it wrong. He got it wrong. Right? So it should be N here and M here. Okay, so let's see. So this should be D of F1. Okay, what do I know? I know that it is this so when I write that, what do I mean? I could see. I could think of this as free module with the generators being dt1, dtn. Right? So let's think again. So on the affine space an, I know that omega is a free module, and I can think of the generators of that being formally symbols dt1 to dtn, right? And what we saw was that when I think of kx, the free module of kx with of course for the affine space it would be the free module over this ring, right? It's a free module over this ring with basis naturally, very cleverly taking the symbols to be dt1, dtn, right? But when I think of the free module over this ring kx with symbols dt1 through dtn, it's as if I am pulling back the cotangent bundle of the affine variety to this subvariety, right? Okay. Now I have to cut it down. This is too big. It's the size I have to cut it down. What do I cut it down by? I look at the images of df1. That's an element of this free module. I quotient by that. Look at df2, quotient by that, and dfm quotient by that. Okay. What are those? df1 is of course del f1 by del t1 dt1, del f1 by del tm dtm. So that is precisely what I mean by the first row. See, the first row is the image of if I think of this matrix. So what is the image? So the first row is, when I think of it here, what do I mean? It is the first entry times the first canonical basis element, this entry times the canonical basis, but that is dt1, this is dtm. So therefore this entry is precisely df1, this is dfm. Okay, I should write n here, n here. Now it's okay. So he did make a mistake. Okay. Okay, now I'm so we are here. So what we have said is that I can think of this omega now as the co-kernel of this matrix, right? And that's what, and let R be the rank of that. Okay, fine. Now, yeah. So what do I want to? I want to now relate to the dimension of x. E is the dimension of x, right? So E is the dimension of X, that is the transcendence degree of the field Kx, I mean K round bracket X over K. Okay. So the part that I will assume from affine algebraic geometry is that dimension of X as a variety is the transcendence degree over K of K of X. Right? Okay. Now so therefore I know this is E. Okay, now let's see. Suppose I want to show this. Okay. Okay, what do I know from this? Let's see. Or rather, let me, instead of doing it my way, let me just follow the book and see what it says. So this is okay, except that he got the M and N switched. Okay. Okay. Now the claim he makes is, okay, here let me do it here. Continue here because we might. I don't want to erase this because we might need it. Okay. So he says dimension of Kx so he claimed right. Okay, let's see why this is true. So what we had proved was, see, now recall, this is a field over another field, right? So what had we proved? If I look at, if I have, so let me, I don't remember what I used, maybe something like this, dimension as an E vector space of this, where E was finitely generated. So the assumption was E was F x1 maybe xm, something like that. Anyway, the point is that it is finitely generated as a field. Now this is bigger than or equal to the transcendence degree of E over F. That's one statement. Second statement was equality holds if separably generated, right? Okay, if E over F is separable or separably generated. Okay, is separably generated what we had, but then later on we proved separability and separably generated were the same. So is separable, let me use. Okay. Now, so what do I get if I apply this? Well, I'll get that this is bigger than or equal to, right? Because the transcendence degree of this over this is precisely the dimension of X. So I get bigger than or equal to. But I want equality. How do I get equality? So I have to show that this is separable over K. What was our definition of separable? If I have linearly independent elements, then I take pth powers of those, then they are linearly independent still, right? Okay. Now the point to observe is, suppose my underlying field is perfect, base field is perfect, then any extension is separable. Because, okay, that's because if say if I take let's say some x1 through xr are linearly independent and over k, and suppose their pth powers were linearly dependent, you write that those coefficients and then you can write these as pth powers and then take the p out, so it would follow that these are linearly dependent. Okay, so but then we are over an algebraically closed field, therefore it's perfect, therefore equality holds here, and therefore equality holds here. Okay, so I'll just write this is because this, and the number was 4.2.9, I think. Yeah, this is 4.2.9, and then kx over k is separable because k is algebraically closed, hence perfect. Okay. Okay. So what do I know? I know that R is equal to where are we? Yeah. Yes.
Don't we need rank of M to be n minus e or
Rank of M A to be?
n minus e?
It will be. That's what we are trying to prove. That's what we are trying to prove. Okay, so what we see, the point is, yeah, that's what we are trying to prove. Okay, so on the this relates the rank. See, in this lemma, the rank is related to various things, right? What this does is it gives me this in terms of E, right? So I have to make sure that when I am talking of this, what is the relation between that and this? Yes, but there is a k round square bracket x there and there is a k round bracket x there. So I have to use my 15 or something, that exact sequence, and make sure that I'm all right, and then show that R is n minus e. That's the point. That's what we are trying to do. Okay. Okay. So let's see. I'll just follow what he says. If R is as before, it follows from 4.3.21 that E equal to n minus R. So let's see what 4.3.21 is. Yeah, well, just you need just one more bit, and that is okay, to make it formally okay, so Okay, what I claim is, okay, he seems to be making one more jump. Okay, so we need to relate. So what he says is that E is equal to n minus r will follow from this. So now what we have is that that the dimension of this is E, right? Okay. Now but is that the co-kernel of this map? That's the question. See, at this level it is the co-kernel. So what I have to see is, one more step we have to do, and that's not very difficult, is the following. We have to see that omega, what is the relation between this and this? Pardon me? Yes. So this is equal to this tensor kx with kx. Indeed, but why? Let's prove that. How would you say that? So this is a claim. So if I do this, then it is done, right? Then it will follow that from this, that E is equal to n minus r, right? So why is this true? Well, one way of seeing this is by writing out. So what do I know? So I have so I think of K. Well, let's see. That's not. No, let's see. That's I'm wrong. Sorry, 1 second. That's not. Okay, this is obvious, right? Because any I can think like this: any derivation of any k derivation into a kx module. Okay, so let us just do this. So this I can do by saying, instead of doing this, so this is as kx modules, right? I want this as kx modules. So I hom into some kx vector space and then show it into an arbitrary kx vector space. So what does that show? That means I am taking derivations, k derivations of kx to a, now this is a kx module, right? This is equal to derivations of k well, this is actually okay. So one more step. See, there is a hom. So I get hom over kx of this into m, which is by the universal property of this module equal to this. Here I have to use one more step, namely this is hom over kx of this module over with m was this is just hom over k this with this into m. right? Once I, by restriction I get a form here, and if I have here, that's precisely one here, but then this is equal to derivations over k of k from kx to m. So what it amounts to showing is that this every derivation here extends uniquely here, right? But that is so because of the quotient rule, right? So this is indeed equal. So I can think of this matrix. So when I pass to kx any of the, so although this is only for k square bracket x, it's also true for k round bracket x or kx f as well for a similar reason. Therefore, now what have I proved? I have proved that on the one hand it is n minus r. So this I can replace by because I know that the co-kernel is precisely, once I take it over k round bracket x, it is just this, and therefore this is dimension. On the other hand, it is E, therefore E is equal to n minus r. So I get from, so okay. Now let's see, there exists an affine open neighborhood. So let's see what he's saying. Now 1 follows from 4.3.23 and 4.2.15, okay, 4.3.23, okay. Okay, so what is 4 point here? So if x is a simple point of x, right, that means what? That means that this holds. Now this r is equal to n minus e. Right? So what does it mean to say a simple point of x? It means the dimension of omega is equal to e. Right? So, well, did I say that convincingly enough? Dimension of? No. No. Not so. See, not when you, it might go up when you pass to quotient. See, when you, if x is a non-simple point, so see there is a difference between, it's okay. So yeah, so it might go up. So it's generically that, meaning on an open set it is equal to E, but it might increase.
So what's the if x is a simple point, dimension of the tangent space is equal to E.
Yes, dimension of, so x is simple, by our definition it means this dimension it must be equal to E. That's our definition, right? Okay. Now which is the same thing as, okay, what is dimension of its derivations of okay. Okay, I see what you're asking. 1 second, let me think and respond. He's saying so if x is a simple point, then okay, then what we have to see is that this holds, right? That's the claim. We have proved that E is equal to n minus r. Okay, so in other words, I have to show that dimension k of this is equal to E. That's what I have to show. Okay, now okay, so a dimension of Tx is equal to E. Just 1 second. Yeah. Okay. So here he makes some yes. So I want to say that okay. So I am going to claim okay. So he in fact he does make some comments before this, so which are relevant. Okay. So what should I erase? Okay, maybe I'll erase this part and write it down again anyway. So we are almost out of time. So okay, so let us look at, so what have I gotten by this map? So I've written, so this is my del Fi by del T j, something like that, right? So the point of this map is that the co-kernel of, so this is A, the co-kernel of A is omega x, which is short for this. Okay. Now what is, so I want to relate this to dimension of Txx. That's what, right? Okay. So this is co-kernel means here I can write that. Correct? Okay. Now, what is so if I tensor this with the point is I can tensor this with the, so there is this map kx to kx. So what I have to do is relate, so I'm going to tensor that, so that is a exact sequence of modules over the ring k square bracket x, correct? Okay. Now if I tensor it with the field kx, it is exact because a tensor product is right exact. Okay, that's what is relevant here. So I can do that. If I do that, then what is this A? This A will become this AX. Right, because that's precisely the tensor product of that. Okay, and therefore what I know is that and then this dimension of this is equal to dimension of okay. So this is meaning E, meaning this has dimension E after a tensor as a kx vector space. That's what it means, right? So what I have is that, let's write this is equal to right. I'm just writing after a tensor. So I wanted to show that this was E. It is enough to show that this is E. Right? Now I claim that this is the same as, this is nothing but the dual of this. That's what I want to claim. So if I take this, that is this space, which is now a kx vector space, is nothing but the dual of this space. See, after all, we have been saying it's a cotangent space. So this has to be the dual of this space, dual over kx, but as a vector space, but those have the same dimension. Okay, so I claim that, okay, maybe we will stop now because it's time, but I will pick this up next time, and next time we will finish 4.3, okay, and move on to 4.4. So how many, we have one more week left, right? One more week of classes left. Okay, so it will help if you 4.4 I will try to start it on, it will require a little bit, there is lots of stuff there. So I will try to spend finish 4.3 by half the midway, or I might just say it's all, let you read 4.3 and go on to 4.4. I might even do that. Okay, so see you then on Friday.